All right. I got the tape turned on. Looks like people are having the winter blues today. Everyone away. Um, so we don't have any homework due tonight, so that's good. And this homework, which is on iterated integrals, double integrals also, and known as double integrals and areas in the plane, which we've still been talking about. Not due to next time, but we still have some more examples for this homework. Okay. Just a few more. And so uh, um, uh, this application of double integrals of computing areas in the plane, not that exciting an application since you guys have been able to do that since probably calculus one. Um, but it's good practice with double integrals, which we're going to apply to another problem. I hope we'll get to it today. If we get through these examples of computing areas in the plane quickly, because this is not really our primary application of double integrals. But before we get to that, and even before we get to that second application of double integrals, the main one, we have to go back today and talk a little bit about the meaning of integration, because I need to firm you guys up on, remind you, or maybe explain it to you for the first time carefully of what's really going on when we do definite integration, right? Okay, as opposed to indefinite integration, which is just finding antiderivatives, which is challenging enough, right? But definite integration, I need to explain a little bit more about exactly what drives that process. You understand that before we get back to 3 dimensions from 2 dimensions. Okay, so just have this homework, right? So you know our schedule. Of course, we're coming here to the end of the semester. I'm sure you're all anticipating that. So you know we have this week, and then we have just Monday next week because that's Thanksgiving week. Am I right? Isn't that Thanksgiving week next week? So um, yeah, Wednesday there's no class. That's right. Yeah, so we don't have class that Wednesday. Um, and then but we do have a week following that, and then a test. I think the last regular test, midterm test, I think is the following Monday. I don't know what the dates are. Right. Um, so we still have a little bit of time left, but things are moving rapidly here um, to the end. Probably, especially in um, your other classes, we get to take a little bit more leisurely pace here, probably than I hope than some of the other classes do. Okay, so anyway, that's how things are. That's how things are going to go. All right, so let's switch back to this again. Not very exciting application of double integrals, and so remember, as I just mentioned, right? We're going to use what one thing we can apply double integrals for is to find certain areas in the plane, right? Like this one, of course, which has an irregular shape. This is so you can use this process, this idea that we're practicing here of applying these double integrals to finding areas, if you have what's called a vertically simple region. Okay, a vertically simple region, and that means that the definition is given in the notes, but that means that the region is enclosed by 2 curves, a curve on top and a curve on bottom, right? And that encloses the entire region. Okay, same curve on the top and same curve on the bottom. So this is a very easy example of, again, what's called a horizontally simple region, right? Because this region is just created by this top curve, right? Or the area between, right, this top curve and this bottom curve. All right. So this idea that we're using to compute this area, which is really the same idea that you used in calculus 1. It's just sort of disguised here in the form of a double integral. So again, this is called the horizontally simple region. Let's see, let me see what the definition of horizontally, I'm sorry, vertically simple region, all right? Because there's also a horizontally simple region. This is a vertically simple region, okay? Because the region is bounded by a single function below and a single function above, right? Okay, so single curve below and single curve above. I'm always mixing horizontally and vertically in these definitions. We'll look at a vertically simple region here in just a second. I mean, a horizontally simple region in just a second. All right, so that's just terminology, but let's actually now start computing this area, right? So remember the way you set this up as a double integral, all right, is first, of course, look at the boundary of the region along the x-axis, right? Okay, for a vertically simple region, look at the boundary of the region along the x-axis. So this region clearly here begins at this intersection point for these two curves, right? Which happens to be pi over 4. And then, of course, the region ends here at the second intersection point of these two curves, which is 5 pi over 4. By the way, the top curve here, the blue curve, that's sine of x, right? And the bottom curve here is the red curve, that's cosine of x. So we have two familiar curves, right? In this particular problem, and they have lots of intersection points, of course, right, where they cross each other. But here we're dealing with this region, right, between pi over 4 on the x-axis, right, and between 5 pi over 4 also on the x-axis. Remember, you can find those intersection points, right, for these two curves just by equating the two formulas for the curves, right? So you would be wanting to solve this equation, sine x equal to cosine x, right? And you know sine x is going to be equal to cosine x, right, at multiples of pi over 4, right? Because sine of pi over 4 and cosine of pi over 4 both square root of 2 over 2, right? Okay. And then at other multiples of pi over 4, like for instance, 5 pi over 4, sine and cosine also are equal, right? Okay. So if you were just shown this picture but weren't given these these boundary values on the x and on the x-axis, you could find them just by solving that equation. Okay. And that one you can solve that one just by inspection, because you know angles where sine x and cosine x are the same, right? So now so how do we set up our integrated integral, right? Our double integral. So the outer integral, its limit. So these are definite integrals, right? Because we're going to come up with a numerical answer here for this area. So we have to put limits of integration on, right? So for the outer integral in this double integral, you will use as the limits of integration here or boundary values on the x-axis. So that would be pi over 4 to 5 pi over 4, right? Okay. And then for the inner integral, right? Okay. You're going to use the curves. Okay. So the formula for those curves, right, will be your upper and lower limits here. So the lower limit would be the formula for the lower curve here, which is cosine of x, right? And the upper limit here would be the formula for the upper curve, which is in this case sine of x. Your integrand now in this application, just for this application, your integrand is just 1. Okay, so you just use an integrand of 1 in computing these areas of these regions. Now, for your order of integration, right? Okay, remember your outer integral corresponds to the x-axis. So in the order of integration, x is going to be second, right? And then y, you would integrate with respect to y first, okay? The way you can sort of remember that, right, is the upper curve and the lower curve, right? Okay, they're bounded by y values, right, determined by your two function formulas, right? Okay, and your outer limits of integration, right, are these are the boundary values along the x-axis, correct? Okay. All right, so you just have to compute that. The rest of this now is just calculus, right? Because you just and arithmetic, because you just have to compute that integral. All right, so can we do that here quickly, just as a reminder of how we do double integrals like this, right? You're going to work inside out, right? So you're going to work on this inside definite integral first, right? And then you need to find the antiderivative of one, of course. What's the antiderivative of one? So that's pretty easy. What now? Yeah, be sure you put y, right, not x, because your variable of integration is y, right? So don't put an x there inadvertently. That will mess things up, okay? And so now we have y, right, okay? And we're going to evaluate that from, well, between these limits of integration, right? So we evaluate that from cosine of x to sine of x. And, well, that's so easy to do, right? Because you just have to plug the two formulas, right? Just have to plug these two expressions in for y, right? So you end up with this second definite integral to compute, right? Just sine of x minus cosine of x, right? And thank God those are the variables x here, right? In these formulas, because you're integrating with respect to x, right? So, well, what is the antiderivative here, Fatine, for sine x minus cosine x? We need that, right? We need to find the antiderivative of the integrand, right? This expression, so that we can plug in the limits of integration into the antiderivative, right? That's how definite integration works. So, I shouldn't say that's how definite integration works, but that's our shortcut, right? To compute this definite integral, correct? Is find the antiderivative of this expression and then compute and then substitute the limits of integration into the antiderivative, right? Remember, that is the fundamental theorem of calculus that tells you, oh, if you want to compute this definite integral, you just have to find this antiderivative, right? And plug the limits of integration into the antiderivative. Okay. Well, finding this antiderivative is pretty straightforward, right? Because I think we just have to go term by term, right? So what's the antiderivative of sine of x, if I can remember that? But minus cosine of x, right? So that's going to be minus the cosine of x, right? And so don't forget the minus sign there. And then what's the antiderivative of cosine of x? Sine of x, right? Don't forget that minus sign is in there also, right? So you have there minus sine of x, right? And now you're just evaluating that, right? From pi over 4 to 5 pi over 4. So we're going to end up here with, I think, a bunch of square roots of 2 over 2, right? Okay. Because when you plug these limits of integration into those functions, you're going to end up with something like a square root of 2 over 2, right? So we have minus the cosine of 5 pi over 4, right? Minus the cosine of 5 pi over 4, minus the sine of 5 pi over 4, right? And then we're going to subtract off minus the cosine of pi over 4, right? Minus the sine of pi over 4. Ooh, lots of minus signs there also. So keeping track of all those minus signs that's a little bit of a headache. Okay. What is the cosine of 5 pi over 4? Where is 5 pi over 4 anyway? I mean, in what quadrant it's 5 pi over 4? Yeah, that's in the third quadrant. The reference angle is going to be pi over 4, right? Obviously. So you just have to think of, well, in the third quadrant, cosine is negative, right? Okay. And the reference angle is pi over 4. So you're going to have square root of 2 over 2 here, but it's going to be negative. But then you got this other minus sign on top of it, right? So doesn't that all just end up with positive square root of 2 over 2? Am I doing that right? What about sine? Yeah, it's also negative square root of 2 over 2, right? But then you've got this minus sign on top of it, right? So so all those minus signs are going to cancel. That's nice. What about in the second parentheses? This one is even easier, right? So cosine of pi over 4, that's obviously the square root of 2 over 2, but now this minus sign stays, right? So we have minus the square root of 2 over 2, and then sine of pi over 4 is same thing, right? So we have another minus square root of 2 over 2. My goodness, what is all of this? Once we get all those minus signs taken care of, this looks like square root of 2 over 2 plus the square root of 2 over 2, right? And then gosh, what happens in here? Well, when you distribute that minus sign, aren't you going to get a bunch of positive square root of 2 over 2's again? Right? That's going to be plus, and that's going to be plus. So wow, it looks like we just have 4 square roots of 2 over 2, right? Which I think is 2 times the square root of 2. Oh, so we end up with 2 times the square root of 2. Oh, so nice answer there. That's maybe, what's 2 times the square root of 2? Approximately 2.8 or something like that, I think. Okay. So yeah. So I think that I rounded to 1 decimal place. I think it's 2.8. So it's a little bit more than 2.8, but rounded to 1 decimal place. So this area apparently is 2.8. Does that seem big enough? Not sure. Okay. But of course, sine and cosine don't get very high, right? They only go up to 1 and minus 1. But this is kind of a long distance, right? A little bit more than 1/2 to a little bit less than 4. So I don't know. Okay. That's one where my intuition kind of fails me. So it's a good thing we have the double integral there, right, to compute that area properly. Okay. But again, that's something that we could have done in calculus 1. Okay. Without using the double integral. Here's an example of this is a horizontally simple region. Okay. Not vertically simple. All right. Because this region is bounded on the left and the right by 2 curves, right? Okay. And then just on the top and the bottom by locations, boundary values on the y-axis. So that's called horizontally simple as opposed to vertically simple. But you can also use the double integral to compute the area for these horizontally simple regions as well. Okay. But so look at these curves though. All right. For both of these curves, in neither case is y a function of x. These are in these curves, y is not a function of x, but x is a function of y in both of these curves. If you turn this picture, rotate this picture, see that x is a function of y value matching x value. Same thing. This is also an option wrong, okay, as opposed to y x. Right? And in that case, then that's called again a horizontally simple region, just bounded horizontally right, left to right by these 2 curves. And so we can also set up a double integral to compute this area as well. All right. You're just going to switch the order of integration. All right. So instead of being a dy dx, the order of integration would be dx first and then dy second. Right. the integrand is going to stay 1, okay? So you always use 1 here as the integrand in computing these regions. So these two-dimensional regions. What should be the limits of integration for the outer integral? So what are the boundaries with respect to y that you see here? See, this is D, yeah. Okay. So C and D, yeah, obviously right. Okay, along the y-axis, you're bounded by C below and D above, right? What about now for the limits of integration on the inside? So what about the limits for x? So how is x bounded? Y is bounded by C and D, right? How is x bounded in this shaded region? Well, what's the upper boundary? It's this curve, correct? And what's the formula for that curve? It's whatever this formula is, okay? Which I just labeled as h sub 2 of y. So notice that's some formula involving the variable y, okay? And what's the lower bound for x? Well, it's this curve, correct? And this lower bound is just whatever this formula is for x, right? Which is h1 of y. So again, notice if you actually try to if you actually go through the steps, right, of evaluating this double integral, starting with the inside integral, right, you would get what? Well, what's the antiderivative of 1? X, right, okay? And then you're evaluating that from this expression involving y, h sub 1 of y, and then the second expression involving y, right? H sub 2 of y. And you just plug those two expressions into your antiderivative. You can do that, right? That's legitimate because these expressions just involve y. So with respect to x, these expressions are just constants, you see, okay? With respect to x, these expressions are just constants, just like C and D are just constants. So when you plug those in there, of course, you get h2 of y, right? Minus h1 of y. And then you want to integrate that with respect to y. That's all going to work beautifully, right? Okay. Right? This is a expression involving y. This is an expression involving y. And you're integrating with respect to y, right? Now, I can't go any further because I don't know what H2 and H1 are, right? Okay, but that's how that double integral process is going to unfold. Okay, let's try one where we actually have to draw the region of integration. And I think we did that. We've drawn regions of integration before, but I don't think in this type of application. Okay, so suppose we want to compute this double integral. So this is supposed to be, that double integral is supposed to represent the area of a region. All right. Okay. And let's see if we can draw the picture of the region that we're computing the area for. Okay. Again, you can sort of tell that that is you can sort of tell that that double integral is computing the area of a region, right? Because what's the integrand? It's invisible. So what is it? What's the integrand right here? 1. Okay. So usually when we have an integrand of 1, at least for this class, we're computing the area of a region, but we're going to use integrands of 1 again a little bit later also to compute volumes, all right, not just areas, okay? Because that's what we're moving to. Want to get to 3 dimensions, obviously, okay, and stop moving around here always in 2 dimensions. All right, so let's draw a picture of this region, and then so at first we're integrating with respect to x first, and then y second, okay, and Then we want to switch the order of integration. So I want to set up a second double integral where I integrate first with respect to y and then with respect to x. So you can tell by this order of integration, what sort of region do we have here? Is it a vertically simple region or a horizontally simple region? Because it's got to be one of the two. This trick doesn't work unless you have these so-called simple regions. Yeah, this is going to be horizontally simple. This is like the previous example, right? Because I'm integrating with respect to x first, right? Notice my limits of integration here are constant with respect to x, right? Of course, this is a constant anyway, but y squared is a constant with respect to x, right? And then we integrate second with respect to y. So this is a horizontally simple, apparently, or horizontally simple region. Let's see if that's true. So I'm going to draw a picture of it. Okay. So look, to draw a picture of this, you can see that this region is going to be bounded along the y-axis by what? 0 and 2, right? Okay. So this region never goes above 2 on the y-axis and never goes below 0 on the y-axis. So it somehow fits in that strip from 0 to 2 along the y-axis. It's not that entire strip, because that entire strip is infinite, to the left and the right. But whatever region we do have there fits into that that little narrow strip, right, between 0 and 2 on the y-axis. But the region is also bounded by these curves. But think of these curves as functions where x is a function of y, where x is a function of y. So to do that, just set it there in the limits of integration. Normally, you don't have to do that, but here it's helpful. So I'm going to write x equals 4 and plot that curve. And then I'm going to write x equal y squared, and I'm going to plot that curve. Okay, or try to plot it. And that will give me the curves that bound this region on the left and the right. Okay, this is a horizontally simple region, so it's bounded from left to right by two curves. Okay, one of them is x equal 4, and the other one is x equal y squared. All right, let's see if we can graph those. Those should be pretty easy, right? X equal 4. What does that look like? This is the vertical line, right? So let me count over 4 here, but I'm going to space my tick marks a little bit. So let's make this 1, this 2, this one 3, and then right here will be 4. So x equal 4 is just this vertical line, right? So see, there's the left curve that's the right curve that's bounding my region, right? And then the other one we want to graph is x equal y squared. X equal y squared, right? So if you want to just make a little a chart here. And just plot a few points. And if you can't immediately see what that's going to be. So let's see, when y is 0, what's x? Also 0, right? So that curve goes through the origin. When y is 1, x is what? Also 1? So right there, right? When y is 2, right? X is 4. So it's going to go up here. Right? Did I do that right? It's x equal, oh yeah, no, is that right? Let's look back at our x equals y squared. So don't I have to? Oh yeah, x equals y squared. So I'm plotting the points incorrectly, right? Okay, all right. When x is 4, y is 2. So I'm here, right? I almost plotted the coordinates backwards. So I'm glad you said something. Okay. Yeah. All right. So this is correct, right? But we have to remember that this is the X and this is the Y, right? So when you're plotting the point, it's this point right here, right? Okay. Well, that's as far as I need to go, right? Because that's as far as I need to go, right? Because the region is bounded here on the left by, on the right by x equals 4. So where is that region? Well, it's just this part in here, correct? Now, by the way, this curve, right, this function, x equal y squared, when you plot that, also comes down here, right? Okay. But that portion, this piece here below, between the curves, right below the x-axis, is not included in the region. Why not? So why am I not shading this portion? Because the y is from 0 to 2, right? Okay. Remember, the limits of integration on the y were 0 to 2, correct? Did I plot that? I didn't plot that point right. Let's try that again. This point is really up here. So my picture is a little bit misleading. Just a little bit. That looks better, right? Okay, so we only have to worry about sort of the top half of that of this area, right? Um, okay, so there's the picture, and that, see, indeed, that is a horizontally simple region, right? It's bounded on the left and the right, right, by just two curves, right? This vertical line and then this parabola, right? This piece of the parabola. All right, so let's set up the double integral, right? So what's that going to look like? So what about our outer limits of integration? Oh, we've already got it, don't we? Ah, there it is, right? Okay. I'm sorry. We already had the integral set up. So um there's the integral for that. Let's try calculating that. Hope it's not too bad. So uh let's try computing this. So again, antiderivative here is really simple. That's just x, right? And we're evaluating that from y squared to 4. So that's not bad. We're going to get what? 4 minus y squared? And now we just have to find the antiderivative of 4 minus y squared. Well, I think we can do that because we just have to use the anti-power rule, right? What's the antiderivative for 4 minus y squared? So the antiderivative of 4 is what? 4y, and the antiderivative of y squared? That's really where you get to use the anti-power rule, right? That's y cubed over 3, right? And now just evaluating that from 0 to 2. Well, thank God 0 is one of our limits of integration, right? That always is a nice limit of integration because when you plug that in, you're going to get 0, right? So you really only have to worry about plugging in the upper limit of integration. So we get 4 times 2 minus 2 cubed over 3. That's going to be the area. So that's 8 minus 8/3, I think. And how much is 8 minus 8/3? 16/3? Is that right? 8 is 24/3 minus 8/3 is 16/3. So looks like the area there that we plotted just 16/3. Now, it's good I drew the double integral though, because the second part of the problem is switch the order of integration. So suppose instead of what was our original order of integration there? Dx dy. So suppose we want dy dx. So that implies that we can treat this as a vertically simple region as well. And is that also a vertically simple region? So is it just bounded above and below by two curves? Yeah, I think so, right? Okay. Yeah, exactly. What's the lower curve there? Yeah, just the x-axis, right? Which is y equals 0. So that's nice. Just 0 for this lower bound. And now what's the upper limit? Well, you have to think of this curve as being a function of x now instead of y. So you said it. What does this look like as a function of x? Yeah, just solve this. Just solve that equation for y, right? So you get y is equal to positive square root of x, okay, because we're only interested in the upper half of that parabola. So this limit of integration is square root of x. What about the limits on the x-axis? Pretty easy, right? Just 0 to 4, right? Okay. This region just runs from 0 to 4 on the x-axis. And again, so nice there, your integrand is just, okay? So apparently if we evaluate this double integral, we should come up also with, we did it right the first time, we should also come up with 16/3, okay? Also should come up with 16/3 there. Now I want to show you one more, but we don't have to go through the whole integration process. We just want to set up the double integrals that define the area, okay? So here we want the area bounded by 4x minus x squared and then 6 minus 3x, those two curves. So one of those is a straight line. This obviously has to be a parabola, right? And the x-axis, okay? So here's a picture of this. And this must be, this obviously must be, what was that? 4x minus x squared, I think. So the blue curve is 4x minus x squared. And then this must be, whatever that line was, 6 minus 3x. If I remember the formulas correctly. Yeah. All right. So we want to find, or we just want to set up. We can do the calculus easily enough, but we just want to set up the double integral for computing this area, right? Okay. Remember, below the boundary is the x-axis. All right. So that shaded area there is what we're interested in. In this picture, you can see easily what this intersection point is. That's kind of important, right? Okay, because you're going to need that to, I think, to set up the limits of integration properly. And you can see that that is what 1 and 3. But so you can just read that off of the graph. But if you didn't know that, right, if the graph weren't marked properly, so you could see the coordinates of that intersection point, of course, how could you find that intersection point? Yeah, just set the two formulas equal to each other and solve, right? That would give you a quadratic equation to solve because you'll have the x squared in the equation, which means you may have two solutions. And indeed, you are going to have two solutions here, right? One of them you just don't see in the picture. There's another intersection point of these two curves right here, somewhere far over on the right, where we cannot see it. But that one's irrelevant to us because our region stops there at the x-axis. So what's the issue with this region, however, and our approach to finding its area, this double integral approach to finding the area here? Because this is not a what? Perfect. Yeah, you got the terminology right there. Yeah, it's not vertically or horizontally simple. Okay. Remember, for it to be a vertically simple region, you have to have a single curve on the top and the bottom that bounds the region. But here, so if you look vertically here, you don't have just a single curve that bounds the region, right? You have two curves, this straight line and then the x-axis, which are separate things, right? And also, it's not horizontally simple either, right? Okay, because if you look from left to right, you have this region is bounded here by, unfortunately, here, right, by itself. Okay, but here the region is bounded by the line. Okay, from left to right. So you don't get either horizontally or a vertically simple region. So that complicates things a little bit. But as Elijah suggested, if we just break this up into two regions, right, we can get two simple regions out of this. How could we do that? So Amber, do you see how to split this up and maybe that two simple vertically simple? Because what about for just this piece? This piece over. Oh, this piece. That is that vertically simple? So just this piece, let me put some extra cross hatching in here. So just this piece. Um, just this piece on the left up to that red line, which is x. So is this piece is it so vertically simple? Yeah, that's right, vertically simple. Because it's bounded on the top bottom just by two. Right? Top, it's the bottom, it's the red. So that is is it over this part is bounded on top. This part is bounded on top. So just with the left part is bounded. Oh, so we can this next part, then don't worry about it. Okay. So Amber, can we set up the integral for this part? Okay, the part, just the crosshatch part here, this part. So the double integral for that piece. So that's vertically simple. So how are you gonna? What's going to be your order of integration? Is it dx dy or dy dx? Well, it's dx dy. Um, so dx dy. Remember, the integrand is always one. So what are the limits for the y-axis? Is it the y-axis? Oh no, do we do this backwards? Yeah, vertically simple, we want dy dx. Okay, but here's how you can remember that. Um, for vertically simple, want the outer limits of integration to correspond boundaries from left. That would be on the x-axis. So x on the second. That's your course onto boundaries on this side. By the way, where does it start at? This piece. From left to right, where does the crosshatch start at? Start at right? Starts here at 1, extends to 1, 2. So for outer limits of integration here would be from 1 to 2. Okay, that's with respect to x. So that means that the inner variable, right, would be y. So on the y-axis, right, on the y-axis, Amber, where does that region start and stop? So this is up and down, right? So where does it start at? It starts at this curve, right? What's the formula for that curve? So it's 6 minus 3x. Yeah, put 6 minus 3x there. You can think of that as being y equals 6 minus 3x, right? Because your variable integration for that inside integral is y. And where does it go up to? What's this one? It's 4x minus x squared, right? The blue curve is 4x minus x squared. Oh, so that piece, this double integral, when you evaluate it, will give you the cross-hatched part, okay? So that's like part of the area, right? I don't want to say half of it, honestly, half of it. Now, what about this piece? So again, that is very simple, right? Because on the bottom, it's bounded by this one curve, which is the x-axis, and bounded by 20 x minus x squared, right? So it also set up double that and then add it into the first double integral, right? And we're done. So so what's this going to look like? Again, your order of integration is going to be dy dx. What are the outside limits of integration for this piece? Where does it start? X-axis. This starts at what? 2 goes up to where? So starts at 2 and goes up to 4. And what about the, of course, the integrand is always 1. What about the y-axis, right? Y values start where? I'm here, right? Go, right? It goes up here. Which is my no. Okay. That's it. So you just have to evaluate those two definitions, right? You'll get some that. Right, so I'm not going to go through that. Manage that part pretty easily. So again, that second integral corresponds to the area on the area on the. Okay, but again, now our goal here is not computing areas. We have bigger things in mind. But to understand how we're going to use double integrals in our second application, I need to remind you a little bit of just what definite integration means, okay? So it's very important you pay attention to what I'm telling you here, okay, everyone, because if you do not, you're going to get lost, okay, in this second application. All right, so this is not a trivial thing, okay? All right, but we have to go back a little bit. We have to step back a little bit and remind ourselves what definite, not indefinite integration, that's just antiderivatives, but what definite integration means, okay? The way we use usually, in practice, the way we use definite integration is to help us compute some amount, okay, to measure some amount that for some reason is difficult to measure. Okay, usually, sometimes amount is regular some way. Right? So again, integration is going to help us measure some quantity. Want to measure but the quantity is for some reason, practice, there's lots of reasons, for some reason the quantity is difficult to measure, right? All right, so integration uses a very simple idea from logic, okay? It's from elementary logic. And you probably know that idea as dividing. So what we're going to do is take this quantity that is for some reason difficult to measure, and we're going to break it up into little pieces. Okay, so we're going to divide it into little pieces that are easier for us to measure, right? Whatever reason. Pieces are easier for us to and then going to combine all those little measurements back together. We're going to add all those measurements back together to get a measurement for the entire earth. Okay, so see, that's the divide and conquer. Divide by difficult quantity to easier to manage smaller quantities. I'll measure those quantities, and then I'll combine all those measurements back together. Then I'll have the measurement different large quantity. Okay. Now, the first application you usually see of that is geometry. Okay, right? That's usually the first application you see of integration. So, so how do we apply this integration idea to a geometry? All right. So, suppose our task here is to measure the area of this green region. Okay. So we want to measure the area of that region. Now, that's a tough problem in geometry. Why? It's not a regular figure, that's right. Okay, so it's not some well-known regular shape, right, from geometry. We know how to find the areas of rectangles, right? We know how to find the areas of circles, and we know how to find the areas of other geometric figures. But all of those are sort of standard, symmetric, regular geometric figures, right? And so we have formulas that have been known, since forever for computing, the areas for lots of geometric figures. But this doesn't fit into. This is not a sort of regular standard geometric figure, right? Mainly because it has that irregular edge here on it, right? Okay, so it's almost a rectangle, except it's got that irregular edge at the top. Okay, all right. So so here's where integration comes into play. All right, here's what we're going to do. We're going to take that irregular area, right, and we're going to subdivide it into shapes that are easy for us to compute the area of. Okay, and normally the way you see this presented is, although it doesn't have to be like this, normally the way you see this presented is we're going to break that area into little rectangles. Okay, because rectangles are easy to compute the area of, right? Okay, because we have a formula from geometry. So we'll break this this big region up into smaller rectangles, compute the area of all those smaller rectangles, and then we'll integrate, add back together all of those smaller areas, and that will give us a measure of large irregular. Okay. Now, notice you are making a trade-off here, though. Notice you are making kind of a trade-off here because you only started wanting to measure one area. But what we're doing is we're breaking that area into lots of smaller areas, each of which we have to measure. So we've taken one kind of big problem, and we've the sacrifice we've made here, the trade-off we've made is we now have lots of problems, right? Because we have to compute lots of different areas. But the trade-off is worth it because each of the smaller areas is easy, right? Because we know how to compute. So you know now from calculus, right, how you play this game, right? So because you've seen this picture many times. So we'll divide our interval here, right? Because that's the extent of that area, right? It's from A to B on the x-axis. So we'll divide that into a bunch of little sub-intervals. Right? Usually we make the subintervals all the same length, but they don't have to be the same length. Okay? They don't have to be the same length. So each one of those subintervals will represent the width of a rectangle. Okay, so I'm going to build a rectangle above each one of these little subintervals. Here's an example of one of them. I just picked one of them. Okay, to illustrate, but actually we have rectangles here above each one of these subintervals. Okay, all right, so that's kind of the width of the each rectangle, right? Is going to be the width of each one of these little subintervals. Right now, how do we get the height of the rectangle? Well, you just simply pick a value out of the that subinterval on the x-axis. You draw up there to the curve, right? You stop at the curve, and you make that the height of the rectangle above that subinterval. Okay, so here just as an illustration, I picked an x value here. I just called it x sub I out of this rectangle, out of this interval, right? So I drew a line up there, a vertical line up to the curve, right? Okay, and that's where I stopped my rectangle, right? So you see that rectangle fits into this kind of fits into this area. So if you draw that same picture, right, for each one of these little subintervals, you'll get a bunch of rectangles that kind of fill up this area, right? Oh, by the way, what is the height of that rectangle? The height of that rectangle. It's f of xi, right? Yeah, sure, right? Because you stop that height there at the curve, right? So this height is f of xi, correct? And what's the width now of each one of these rectangles? Well, the width could vary, by the way, but just to make our life simple, let's assume that all the widths are the same. So let's assume that we've broken this interval from A to B. Let's assume we broke it into equal size intervals. So what would be the width there? What would be this width of this this rectangle? Well, you have to, it depends on how many rectangles you want to put in here, right? Okay. The more rectangles you put in, the skinnier each one is going to be. All right. So normally you let the normally just for notational purposes, let's let n be the number of rectangles, right? So you would just take the length of this long interval, which is b minus a, and divide it by the number of rectangles that you've put in there. Okay. And that would give you the width of each rectangle. So, of course, how do you compute the area of the rectangle? Yeah, it's just length times width, right? Okay, just length times width. So what will be your estimate, right, for the whole area of this green region? What would you do again? So you broke it up into all of rectangles. I didn't draw them all. Rectangle. All these areas in what? Yeah, you add them up, right? Okay, and that gives you your estimate. But now you know, of course, that this is a little bit. This estimate is going to be just an estimate, right? It's going to cost because you cannot fill up this region exactly with these rectangles, correct? Right? Okay. You can already see this rectangle doesn't quite fit into this area properly, right? Okay. It's a little bit short here, and it's a little bit on this side, a little tall on this side. So when you add up all of the areas of all rectangle, you get a good estimate. You don't get area. All right, so let's see what we've done here. So let's write this down notationally. All right, so my estimate for my area, this is just an estimate now, right? Remember, you're going to add up. So you know there's our summation of area of all these rectangles. What are the area of all these rectangles? Well, let's see. It's the height of every rectangle, right? Which we said was f sub xi. times the width of every rectangle. I'm going to call that delta x, width of the rectangle. Remember, the way you compute that is just take that total interval from A to B and divide it by the number of rectangles. Okay, add all, so that's the area of each rectangle. Right? Add all those up, and you get add all n of those areas up. Get estimate. Now, of course, that's just an estimate, right, Elijah? So here's where calculus. But this is all elementary. So go for it. Okay, calculus here. But where does calculus come? So calculus comes into play as going to try to get a better estimate, right? And how do we get so now averaging is it's a good way of getting estimates, but it doesn't quite apply to this situation. Take calculus here. But now what we're doing here is integration, but we haven't got to the integration part, right? Then it drops, okay? Then it's going to that fundamental idea from calculus of limits. How do we get a limit out of this? By choosing more and more rectangles. So, right? All right. By just picking more and more rectangles. How do you get more and more rectangles? Remember, the number of rectangles is what? I'm calling that n. So you just let that number n do what? Yeah, go to infinity. Okay. And now, you, of course, you physically cannot let n go to infinity, but this is where imagination of it comes in. Because you can think about, right? What calculus allows you to think about what happens, right, as that number of rectangles goes to infinity. Okay? And you know, figure that. Okay? This is what's going to happen if number of rectangles goes to C happen. Okay, so that's exactly what to compute it. Notice this is not an equal. This is exactly. Compute the area exactly. Going to let the number of rectangles go to infinity. This expression, number of rectangles is going to be larger. Okay. You don't have to do those calculations by hand. Okay. Because you can imagine be able to see from the expressions. Oh, I can see what's going to happen. N gets larger. By the way, as n gets larger and larger, the width of each rectangle is getting smaller, right? And you get more rectangles, each rectangle smaller and smaller. So another way of writing this limit is usually the way you'll see it. Instead of letting n go infinity, think about what happens when width of each rectangle goes to C. And the width of each rectangle is really small, you're going to have lots of rectangles, right? Okay. So as the width of each rectangle is 0, that means the number of rectangles goes to infinity, as you got to fill up your whole area of rectangles. Okay. So this limit, computing this limit, is exactly calculus area. Right? And our intuition, this is really where separate you from dogs. But because your human brain allows you to see, conceptualize, to figure out, oh, what's going to happen in this expression. Visual. What's going to happen in this expression? Number of rectangles. This limit now, that's kind of cumbersome to write all that out. So we have shorthand. Okay. Instead of writing limit, that's really cumbersome. Just writing this. Here's okay. So that integral sign is just a shorthand. Instead of writing delta x, write dx. Right? And if it's an integration there, of course, well, that's that's involved in getting the width of each rectangle. Okay, so that delta x goes to 0, sort of. So remember this integral, this definite integral, is really just shorthand. Now, what makes that easy, what makes this definite integral easy to compute is really important idea from the first semester of calculus. You can calculate this definite integral if you know what. So you don't have to do any computations. You don't have to make any guesswork. You can compute this definite integral if you know what antiderivative. Turns out that actually calculates it. All you have to do is plug in down take the difference. Oh, and that gives the okay. That's the calculus. Now, but I want you to think of this. I want you to think of this calculation in a particular way. What we're really doing here is we're filling up this. Really doing here. Not what we're really. Here's how I want you to think of this integral as filling up that area with a bunch of rectangles, but where the rectangles are infinitesimally small. Rectangles are small. So you're filling up that area, a bunch of infinitesimally small rectangles. What's the width of an infinitesimally infinitesimally skinny rectangle? What's its width? What's width is infinitesimal. Right? How many of these infinitesimal rectangles have? We have infinitely many. Okay, that's what that definitely okay, adding up a bunch of infinitely thin. Here's their width. The width is infinitely thin rectangles. Okay. So if you sort of converted that picture to a calculus picture, would be filling up this whole area with a bunch of infinitesimally thin rectangles. Here's their width. Okay, how many of them are there? There are infinitely many. All right. So of course we can't really draw infinitely many in here, but I can't draw that, but I can think of that. Okay, I can conceive of that process. Now we're going to get back to this in just a second. This idea of kind of infinitely many, infinitesimally small things filling up some sort of quantity. Did you already know that about definite integration? Did y'all know that's what definite integration was? Kind of. Okay. Yeah, you're really going to understand it better and shortly. All right. I have one other aside now that is just about geometry. Well, it's a little bit of calculus too. Okay. That we also need. So I have a question. All right. Suppose I want to compute the volume of that box. You want to compute the volume of that box. Okay. But here's what I'm going to tell you, right, about that box. So normally, of course, you would want the link. Here's what I'm going to tell you. I'm going to tell you this square that is this face of the box, the square that is the face of this box, that's a two-dimensional square. Okay, face here is a two-dimensional square. I'm going to tell you what its area is. Its area is 10 cubic. So, see what I'm saying? Area of this face of this box, which is this square, this area is 10. And the length of this box is so I'm going to write down a formula for the volume of that box. Yeah, what is it, Robert? Should be easy, right? What now? The area of the base, right? Okay. So you're calling this the base, this face the base. So what is that area? 10, right? Times what? Well, but in this picture, the length right down. Okay. Just how much? Just now, I don't know it's not. So you just take the 10 and multiply by the. That makes perfect sense, right? From your knowledge of boxes. Because after all, how you can length times width times height, right? Well, here you know the width and the height, right? Sort of, because they've already been multiplied together in this situation, right? Multiply the width and the height together, so already got 10, because that's going to be the area of space, correct? Right? And then we just have to multiply. Okay, so that's kind of that volume calculation is kind of easy. But my point here is this same idea applies to lots of different other shapes, not just boxes. So suppose you had this, and you wanted its volume. That's not a shape from elementary geometry, right? Okay. So how would look if we get lucky? So, but we're told, oh, the area of this space, okay, area of space is, and how is this object constructed? It's just kind of what this same area, right? Sort of heated, right? For a particular length. Any cross section you cut here of this object, a vertical cross section you cut here of this object, is going to give you the same area. So that means then that all you exactly the same way from the box. All you need is make this area of space will find. So the volume here is the same as it is for the box, okay? It's just L times, I'm sorry, it's just 10 times L. Just that easy. By the way, this, no, this figure, we're talking about this. So, and rectangles also normally think so. Figure faces a circle, but then have a circle. All right, now let me show you another cylinder. I want you to compute also its volume. All right, so see what they it's like a prism, except this space is not quite a triangle. Space is not quite a triangle. So I've got that figure sort of positioned there or situated. It's kind of in 3 dimensions, but the face is on the XY axis. The space is on the XY axis. So the X axis. So how do I compute volume that almost prism? This works. That's not quite a triangle. This edge, this edge follows this 9 minus x squared. That. Okay. Well, it's the same idea as in the previous 2 examples, right? What do you need to know? You need to know that this area, right, which is an area in the XY plane. So you need this area and then just do what with it? Yeah, multiply it times the length, right? Okay, so if we can compute this area, all we have to do is just multiply it by the length, and there you've got it, right? But now, how do you compute that area? That area is not a triangle. If that were a triangle, I figure out how to use an integral. Sure, right? Okay. Yeah. So this is sort of practical integral. Just this area, and then just take that. So let's set up the expression for computing that area. That's going to be what? A definite integral, right? So what's that definite integral going to be? Pretty easy, correct? Just what? What are the limits of integration on the x-axis here? 0 to 6, right? And we want the area beneath this curve, right? So we just write the formula for the curve. So that's 9 minus x squared over 4, right? So that definite integral represents this area. And then I just have to take all of that, right, and do what? Multiply it by L, right? Okay. So we just compute that area and multiply it by L, and that will give us the volume. So I'm not actually going to compute that definite integral for you. Y'all can do that really easily, right? But just calculate that definite integral. Yeah, this is exactly the problem that we're taking up. We want to compute volumes. And this idea that I'm just illustrating here is going to help us with that. Okay, let's jump right to our example because I'm going to give you now a trickier volume to compute. All right, so this volume is bounded by, it's what you see in this picture, right? So it's bounded by the XZ plane, right? See the XZ is the x-axis, right? So it's bounded sort of over here on the left by the XZ plane. So this object is really, okay? This object is in this face here on the left-hand side is just the XZ, okay? And then here behind that face is the YZ. And then, of course, the floor of the object is on the XY plane, right? Okay. But just want beneath this plane, plane, which is that you can see. So you have to figure out how you look like it. So it's a prism like object. Okay. Stopped over here by the XZ plane, stopped behind by the YZ plane. On bottom, sits right on the XY plane, but the face that is facing us, right? This tilted plane that we see right here. Now we do need to know the equation for that plane, so right? And there's the equation for that plane. C equals that's not so. So but I do want to. It's possible that somewhere working some dusty somewhere. Okay, I would search on that. So so app see So this is a configuration. So what is configuration now? Then what's sort of key idea configuration? Where we have some quantity, right, that we're trying to measure. Quantity are we trying to measure? Volume, right? Yeah, we're trying to volume, right? But for some reason, it's some sort of irregular quantity, right? It's a quantity not too present. So, and that's exactly the situation. I want to compute volume. I don't know a formula to apply. So, what does integration say? As one strategy to solve this problem. One strategy to solve the problem. Let's say
Cross section.
well, yeah, we'll worry about the infinite later, right? But we're just going to split it up into what some pieces, right? Okay, that we can measure. Pieces that we can measure, and then measure those pieces, right? And then add those all back together. Okay, that will give us at least an estimate for our volume. And then, Elijah, then this is when we that's all just written. But then where's the calculus? I mean, yes, yeah. So you said we're going to break this up into some pieces that we measure the volume of each of the pieces. Then we'll add those back together to the volume of the prism. Okay. All of that is all just this calculus. Yes, with the limits, but how do the limits come about? So we broken it into pieces, right? Have pieces that pieces. Right? So we add them up, right? Add up the volume of each of the little pieces, and that gives us an estimate for our prism volume. But how do we get our? That's just an estimate. How do we get? I mean, yeah, but limit of what?
Section.
If I recross that, infinitely many pieces. So break our prism into pieces that we can measure, right? Okay, and then we think about what happens when we start having or any pieces, or what happens as what's the limit as we get into. Okay, that's where the limit to infinity shows up. Okay, before that, it's all just written adding volumes. Okay, yeah. So how do we get back? Okay, so back to now. So how are we getting volume of a piece that we can measure? So here's what I suggest. All right. Let's take out here. So here's the x-axis, right? So I'm gonna pick we're gonna split this up into Elijah called them cross sections. All right, that's a good way to do it. That's a good way to say it. Let's let's cut this some vertical. Okay. Not to you can think of cutting it some think of it cutting it. Now, however, you gotta be careful when you're breaking this up, right? If you just cut along lines, you're gonna get just a bunch of little prisms, and I don't know how to measure their volumes equally. Okay? So I have to get a kind of regular shape that I can measure volume. So I'm not gonna quite cut, I'm not gonna quite break the prism up on these lines, right? Cut for this, okay? Because I want those, but I'm gonna break it up into kind of little wedges here. But I want those wedges to be something that I can measure, something I can on. Okay. So my point is, I I cut just like I cut down just along these lines. I'm gonna get a wedge, but unfortunately, notice this edge of this edge is not straight. Okay, that makes it hard to. So I want to cut it into wedges, but I want tops of the wedges to be flat. Right? Let me see if I can draw that in here. It's kind of like breaking the area up into the rectangles where the top of the rectangles are flat, right? Okay. Same thing here. Let me see if I can draw this picture. Probably not going to be able to draw a very good picture of this. Same thing along this edge also. You've got the same problem. Ooh, not bad though. I didn't do too badly. Can y'all see kind of that wedge that I'm going to sort of fill in here into this? I want the top of the edge though to be flat and parallel to X, Y. And I want this edge also square IC. Okay. So notice that you'll see that wedge like this. So see that wedge doesn't quite fit perfectly into the prism. Right? Here's a picture of it taken out of the prism. Not quite drawn to scale. Gonna try to fit that wedge in. And I'm going to do that a bunch of times, right? I'm going to fit a bunch of just like this into a bunch of like this. All the wedges won't have the same size. These wedges back here will be large, but they'll all have the same regular type shape. And I'm hoping I can volume. Y'all are going to have to see if I can calculate. All right. And then, so I'll fill up a bunch of these wedges into a bunch of these wedges. So calculate the volume separately, add them together. That will give me an estimate, not a good estimate, right? For the volume back. So, but first, I have to figure out my volume set. Well, that wedge, though, is a cylinder. Let's notice that every cross section, that cross section is just like this face, right? So how can I the area of this space and this part just multiply it by that's what we're gonna call that we're multiplying in here. Notice, by the way, that length is along the x-axis, right? So I'm going to call this delta x. All right. I'm going to break this x-axis into a bunch of sub and all of this same length. Okay. I'm going to call that course, how do I get a better estimate? Volume by filling up this prism with more of these little wedges, right? How do I get more of the wedges? By letting this, right? Zero. So as the width of each one, or the length, I should say, each one of the wedges shorter, gonna have more and more of it, right? So they're gonna give you a tighter fit prism. Okay, so this I'm just gonna give as a variable. What about this? That yeah, that's okay. That's the that's an area that how can that's a two-dimensional area. So how can you calculate that two-dimensional area? What do we use from calculus to compute? So, integral, right? Okay. So we're going to compute this area, and okay, I just got to figure out how to set up the. Just got to figure out how to set up that integral. All right, let's see. So think of that as think of this as think of this of this okay. If you had that wedge right sort of lodged into this picture, that links right, correct? So that runs along what axis? It's not the x-axis, this is the x-axis. So that link extends on what axis? Y-axis. Where does it start at on the y-axis? Starts at 0, right? Okay. So if we sort of superimpose the axis in this picture, we got just enough time to do this. So if we superimpose the axis, this is the y-axis. Okay, where does it start at? 0, goes up to this point right here, right? So we need to figure out what is y-axis. That point lies on what? On this line, correct? That point lies on this line, which is in the xy plane. So what's the equation? XY. That's called the trace, right? So what's the trace of this plane that intersects with xy plane? Make z0. There's the plane. So just set z 0. Ooh, when you set z to 0, so nice there, you just get a formula with x and y, right? So that is just the equation for this line, okay? So what are the coordinates for this point at a chosen value for x, right? What is y going to be? Solve this for y. I think you'll get 2y is 3 minus x, or y is 3 minus x over 2. Oh, okay. So that point is x and 3 minus x over 2. So right here, this is 3 minus x over 2. Oh, cool. So to find this area of this face, you're going to find an integral that goes from 0 to 3 minus x over 2. Now, The other thing, of course, you need to know is what is the formula for this line? Okay. In other words, what is the expression that we're integrating, right? What is this formula? In other words, what's the height of this face? Okay. It's determined by x matrix. See, at a given, the y is running from 0 minus x over 2, right? So at a particular value y, what at a particular value y, what height? This is going up to the plane, right? So how do you height of height of the plane is just what? It's just z, right? But how do you can see? This is 3 minus x minus. So what goes in is just this. Because that is the term. Okay. So value is I. So I claim that this inner represents this multiplied by what? Delta x, right? Okay. So you just take all of this, that area, right, and multiply it by multiply it by the way, this is dy, right? So by y. Okay. Yeah, you guys told me. So I fill up my prism with lots of wedges. That would estimate volume, right? Okay. But how do I get better estimate? By using what? Make delta x smaller, right? Okay. Which gives you more wedges. So we're going to take the limit here as delta x goes to 0, right? Of a bunch of wedges. So you add up a bunch of volumes of wedges, right? Okay. Add up a bunch of volumes of wedges. Take the limit as smaller than eventually you'll exactly volume. But what is that outer limit? What's the name for that outer? It's an integral. Right, okay. That's just that looks like integration. Right, limit is delta x. Delta x, right? Okay. That's just. So that's the volume. But what is that? That's the volume. But what is that integral? All right, so let's write it down. You said it, Robert. What? It's what? It's the integral from what to what? Yeah, A to B. But what's A and B? Yeah, you're looking at the x-axis, right? The x-axis. So it's 0 to. So the outer is the integral from 0 to 3 of this thing. It's a double integral. So, we're 2 minutes here. Let's summarize. What did we so? So what did we really do? We broke this prism right into wedges, calculated volume of wedges, and added all together. And then we thought about what happened when the wedges became very small, right? Okay. So essentially, we filled up this prism with a bunch of little slices. I infinitesimally thin slices. I always think fill this up with thin bony slices, right? Okay, like this. Okay. Um, and all we really need to know for each slice is what? Its area. Okay. And you're going to multiply it times its length, but really letting the length get infinitesimally. That's so what we're really doing is just cutting this prism into really tiny slices, calculating the area of each of the slice, right? And then integrate. Okay. Could have done that in two ways. Also, take the slices this way. Yeah, I slice like this. Also, slices parallel um, X and Z. Instead of making the slices parallel to I, Z. And also would give me double integral. What would change? Well, that's right. The order of position switched to right from 5x to x to 5, right? So we didn't even get a chance to calculate this. Right? That's the part. The calculations actually part, although it is a little also the hard part is that one. But really just efficient, right? Just breaking volume into pieces, okay, and defining how you're going to make it. That's all right. Yeah. So that's a little bit using it first, but when we start doing, for example, we get really good at how you slicing this. Just okay. It gets to be pretty. Um, um, okay. All right. So, well, we got to stop there now. So we need to finish calculating this one and then do some more samples next time. All right. I don't think I am on my tape at all because I stood over there the entire time. Well, too bad.